everyone. I'm Ravi. I'm a principal engineer in Intel's data center and AI group, and we're going to talk to you about addressing microservices and their challenges with Intel's next generation Xeon processor. And I'm joined by my colleagues Mahesh and Suresh, and we also have Christina from Cornell who will be helping us with this. Okay, so we're going to really go through these areas in terms of what microservices are, why they're important, their challenges in terms of a real world industry and how they're getting deployed, the workloads that can be used to characterize them, and some of the details in terms of how to break down the latency and the observability, how to improve and optimize performance, and also how it is relevant to the next generation processor called Sapphire Rapids. So why are microservices important? So microservices design patterns have been in the industry for a while now. They are quite common in the cloud. And as the chart below shows, there is definite increase in complexity. And this comes with the ability to have much higher scale and much higher flexibility. So in a monolithic setup, what you end up in is all of the functionality inside an application and the scaling and the availability of that workload for saying, for example, to respond to more user requests or more load depends on the underlying hardware. With microservices, you have the characteristics listed on the right, which allow much broader scaling. You're not fixed or dependent on only the underlying hardware or individual system. There are also well-defined interfaces and APIs that let you make it loosely coupled so that you can actually implement different services in different technologies, update them at different times, and so on, which gives it a lot of flexibility. And serverless or functions are further along in that same spectrum that allow even more flexibility and scale with added complexity. And it isn't intended to imply that one will replace the other. They will all coexist, and there is a lot of adaptability happening. For example, we see monoliths becoming more modular, and that is something that is expected to continue. Going on to the challenges that we see. From a microservice point of view, the primary challenge is really around performance and what we describe as tail latency, or the 99th percentile of requests meeting a latency SLA of, say, 100 microseconds. And that is very hard to achieve in a distributed large-scale microservice deployment. And that is something that is overcome normally by either over provisioning, meaning you allocate more resources than you strictly require so that you account for that, or you do a priori provisioning, which means there's idle cycles waiting for additional requests to come in to ensure that you don't violate a latency constraint. This also leads to an observability challenge, because what happens then is you want to record every possible minutiae of detail and metric so that you know what happened for services that are no longer around, to be able to debug, to track how you're doing against these SLAs, as well as troubleshoot. And so that is a significant challenge, and we'll talk about how we can address that. And infrastructure overhead is fairly well known. The fact that you have all of these microservices that need to communicate with each other, that have a lot of orchestration dependencies, that need monitoring, that need scheduling, and all of the other overhead associated with it is a challenge, which means the amount of compute being used for actual useful work, if you will, versus overhead is not a good ratio and not a good balance. And as the comments below show, you have these kinds of challenges well recognized throughout the industry. And as you can see in the diagram, that is a representative look of something that would be used for, say, Kubernetes-based deployment. You have challenges that affect different areas. Memset, for example, is something that you need to do every time a new container or a VM needs to spin up and or needs to be thrown away so that memory is unallocated, and all the other areas of infrastructure challenges and observability challenges. And how do we characterize these things? The challenge now comes into one of which workloads to use, and that's where we've been doing a lot of work with Cornell University and the suite of workloads from them called Death Star Bench, which I like the name. And they have had starting to have broad adoption. And this is an area where we would like to have much broader community partnership as well. The table in this slide shows a mapping of Death Star Bench and its software components to the use cases that you would see in the real world, in terms of the methods used for scaling, the mechanism for deployment, the market segment that it addresses, and the system affinity that it has, as an example, and the software layers that it uses, which are also all open source and fairly common in most microservices deployments. Next, you'll hear from Christina, who's the professor at Cornell who initiated this, and her work continues to work on this, and followed by Mahesh, who will talk about the latency characterization.
Hello, everyone. My name is Christina Delimitru from Cornell University, and I'll tell you a little bit about the work we've been doing on designing a set of representative applications using microservices and the use cases they have enabled. So first of all, I'm sure you're all familiar with the transition from monoliths to microservices. There are several good reasons why that has happened. Primarily, the modularity of microservices makes cloud applications easier to understand, faster to develop and deploy. It also enables on-demand provisioning and elasticity, and it enables some heterogeneity on the software side, either at the language or programming framework level. At the same time, that doesn't mean that microservices do not come with their own challenges. Specifically, we've replaced one large application with a graph of, in many cases, hundreds, if not thousands, of individual microservices, each of them with its own resource requirements. Also, microservices talk to each other over the network, which puts more pressure on low latency, high bandwidth network communication. And even though they're loosely coupled, they still depend on each other. And those dependencies can introduce cascading performance issues, which complicate cluster management. So a few years back, we saw this trend of moving from monoliths to microservices, and we wanted to study what are the implications of microservices across the system stack, from hardware design, operating systems and networking, cluster management, and application and programming framework design. And we also wanted to see how these implications change when you run at a large scale. So of course, anytime you want to do a study like this, you need representative applications built with a specific programming framework, in this case, microservices. And even though there's been a lot of good work in cloud benchmarking in the architecture and systems communities, this work primarily focuses on monolithic applications or applications with a few tiers. And a lot of the interesting implications that we wanted to study only emerged when you have at least a few tens of tiers per application. So for that reason, over the past few years, we've designed the Death Star Bench suite, which is called Death Star Bench because the figures on the right are affectionately known as Death Star graphs. They describe the dependencies between microservices in an end-to-end application. And the benchmark suite focuses on large-scale microservices that stress the typical data center design. Here are some of the design principles that we used when designing these applications. We relied on open source components whenever possible, either for individual microservices or the APIs between them. We made the applications extensible and reconfigurable so that if other researchers wanted to focus on different aspects of the design, they could do that easily. And we tried to capture diverse behaviors from production systems that have been public about their use of microservices. So here's the current status of the benchmark suite. It has 7 end-to-end applications, each of them with tens of unique microservices, and they range from social networks, media services, hotel reservation sites, all the way to drone coordination systems, which involve collaboration between a backend cloud and edge devices. A lot of these services are currently open source, so if this is an area that you're interested in, we always welcome feedback and contributions. So what I'll do is give you a couple of examples of what some of these applications look like, and then some of the use cases they have enabled. Here's the example of the social network. So from left to right, a user request would first hit the front-end tiers, then a set of logic tiers, and then the backend services in memory and persistent storage. And depending on what type of request the user is sending, a different fraction of that graph would be involved. This is if they're logging in or signing up for an account. This is if they're composing a new post and potentially adding images, videos, tags to other users, and so on. The other services also have a similar structure from front-end to logic to back-end tiers. This is the example for a media service where users can browse information about movies, stream them, and write their own reviews. Now, having these applications has enabled a wealth of use cases across the system stack, from hardware design to cluster management, programming frameworks, and application design. So the first thing we did was study the implications that this programming framework has across the system stack. And here are 3 key takeaways out of a longer list of the characterization study, which you can find in the paper in the bottom. So one of the takeaways was that we found microservices to be much more sensitive to performance unpredictability compared to traditional cloud applications. Second, we found that microservices spend, in many cases, the majority of their individual latency processing network requests as opposed to application logic. And we also found that even though microservices are loosely coupled, the dependencies between them can introduce cascading performance issues that are difficult to diagnose and difficult to recover from. These observations have motivated two, among other projects. The first is on a hardware acceleration fabric for networking. So we designed Dagger, which is an FPGA-based RPC acceleration fabric. It relies on a tightly coupled FPGA to the main CPU to offload the entire RPC stack to the FPGA. And the networking interface is also reconfigurable so that we can customize it to the needs of individual microservices. And this is an approach that's not only specific to networking, it can also be extended to other types of common functionality across microservices. The second project that I briefly wanted to touch upon is one that tries to address the impact of dependencies between microservices by using machine learning. So instead of waiting until after there is a performance issue to try and take action and recover from it, SEER tries to apply machine learning to the massive amount of tracing information the cloud already collects to identify patterns in space and in time that signal that there will be an upcoming QoS violation. And as long as we can detect that early enough, we can apply proactive action and avoid it altogether. So not only have we found that this system is very accurate in identifying the root cause of performance issues, it's also explainable, which is what the figure on the right is showing. This is from a 2-month deployment of the social network application in a cluster at Cornell, driven by real user traffic. And not only was SEER able to identify performance issues due to resource provisioning reasons, it was also able to identify performance issues due to design bugs that the developers of these applications were not able to find themselves. So to briefly conclude, there's an increasing trend of moving from monolithic designs to microservices. DeathStar Bench is an open source effort that started out of Cornell to study microservices using representative end-to-end applications. It has since enabled a large number of projects, both at Cornell and in other institutions across the system stack, from hardware design and acceleration to resource management, debugging, and even DSLs for microservices. You can find more information on the applications at the first link in the bottom and more information on the research projects at the final link. Thank you.
Hi, this is Mahesh. I am from Intel Labs. And what I'm going to talk about is, now that we have seen what the microservices are and have seen a video about one example of it, how do we actually go about analyzing these microservices? So traditionally, if when we are doing performance analysis, one would ask questions like, what is limiting my runtime, or what is limiting the throughput of my application, or why is my CPU utilization what it is, right? However, when we go to microservices, we need to make sure that we are able to address additional questions, such as what are the key contributors to the tail latency of my application, or what is causing the problems with scaling it out, right? That's what we need to be able to address. And it's especially challenging in case of microservices because of their highly fragmented and distributed nature, which present a variety of potential bottleneck points. Going back to the same example that we saw earlier of DeathStar Bench social network, present a whole set of you can see the amount of connectivity and potential bottleneck points. For example, there might be microservices that are shared by a number of flows, creating very high fan-in or fan-out points. Or because of this highly fragmented nature, there is a lot of data transfer across microservices, either in memory or over the network, if your microservices are located across different nodes. Or your database backend might be inadequately provisioned. And this is really what we need to be able to address beyond what we have done traditionally. And that really needs a fresh approach for analysis, but not only that, also for platform optimization as well. So digging a bit more deep on this, when we are doing traditional analysis, we typically use application metrics such as throughput or frames per second and couple those with the hardware characteristics at node level. And Intel has a large set of performance counters that software developers and platform developers have traditionally used to be able to optimize their platforms and software. In case of microservices, though, we can add other sources of telemetry. Especially in terms of performance counters, we need to move from node level to container level metrics, whether be it network traffic or memory and so on. In addition, we can take as an input the telemetry that comes from the deployment framework itself, like Kubernetes, service logs or container logs, as well as service allocations, that is, which services are allocated to which nodes. So you can see that there is a lot of new telemetry that we need to consume in a more holistic way to be able to hierarchically address these bottlenecks. And that's what we have set out to do in terms of a new capability we are developing called Micro Analyzer. It will create new analysis methods for microservices, and it will identify opportunities for acceleration and offload. And it goes without saying that this will complement existing Intel tools such as vTune Profiler and Perspect. So let's just focus on one specific part of this microanalyzer framework, and that's related to application tracing. So the application traces here are composed of a tree of spans, where a span captures the latency of individual instrumented microservice or individual instrumented functions even within a microservice. And these are typically exposed by agents, tracing agents. For example, Jaeger agent, which is based on or compatible with OpenTelemetry. And these agents, which are sitting in the microservices, export the logs, which are collected by a trace collector. What we have done on top of that is we have written a retriever that can extract these logs, and then we can do all sorts of offline analysis that will guide us to the bottlenecks. For example, we can do individual microservice latency analysis, such as statistics, looking at the tails especially. Moreover, we can do queue inspection, where the queues are building up and how they are affecting the throughput. We can do analysis on the localization of a microservice. For example, if it's co-located, what kind of latencies we see versus when those are not co-located. And of course, we can do all of this cross-run, which really helps us into building insights into what is happening in the platform as we vary the load or as we vary the allocated hardware. So in the next couple of slides, I'm just going to give you a flavor of this through two examples. First example that we are going to look at is related to tail latency. That is extremely important in this context. So what we see here is a sorted view of all requests in a particular run, sorted with the latency of a specific high-level microservice, which is sending data back to the client. It shows a very pronounced tail, but if we can get a different view of the same data, we can see that that particular tail happens at the beginning of my run in the timeline view. So that already gives me some idea of what might be happening. However, we can zoom into that, and that can tell us that all the spikes actually which are inside the tail are related to the Redis backend. We can go even deeper than this. I'm not going to cover that in this presentation. However, the analysis will print out a lot more statistics as well as debug information that can help you both in terms of software and hardware zeroing in. The next example that we are going to look at is related to throughput instead of the tail latency. Before we go there, just a note that given this highly distributed nature, we actually do see varying bottlenecks at different loads, different topologies, or even different metrics that one might be interested in. So in this case, if you want to look at why my throughput is limited in this particular application, which is again social network from desktop bench, what I've shown here, and let's just focus on the two curves, the green curve and the magenta curve. The green curve is the client for the whole read home timeline service, which is in the social network. And the magenta is the server, which is actually doing the application logic and all the backend therein. We can see that there is a significant gap, which might be what's limiting a number of our throughput or other issues. Right? Moreover, if we look at how this particular gap scales, as we increase the number of clients, we can see that it increases linearly, and disproportionately in comparison to how the server actually scales. The orange here is the server, the blue is the client side. So we can see all this wasted work. And what this wasted work is causing is it's going to offset any benefits of parallelism that you are going to get through these additional clients, limiting the throughput. And this is the kind of analysis that is extremely valuable, whether you are a software developer or a hardware platform developer or even a system engineer. So I think I will stop here and I will hand over to Suresh, who will now cover more in terms of software optimization.
Thank you, Mahesh. This is Suresh. I'm from the Intel Software Technology Group. What I'm going to be talking about is also with microservices, when you're able to try to understand the bottlenecks using traditional methods, then you'll find a lot of very interesting things. So let's first talk about the top-down microarchitectural methodology. So the TMA methodology is a well-known methodology on Intel CPUs that does a cycle accounting or CPI breakdown. Right? And I'll show you an illustrative example now with the Death Star bench. So you can see that the TMA breaks down the execution into 4 buckets. The front-end bucket, where the CPU is stalled waiting for instruction fetches. The back-end, where it is stalled waiting either on memory or execution resources. Or bad speculation, where it goes, it executes some piece of instructions and they're not used anymore. Or the eventual ones, which are the ones that are retiring. So in this workload, you can see that almost 71% of the instructions, the CPU is stalled during this workload execution. And this is a snapshot from one of the nodes on a Cascade Lake cluster when we are running the Death Star bench hotel reservation workload. And let's zoom into this a little bit more. So we can see that the front end, we are having high front end issues due to instruction fetch problems as well as instruction TLB problem. And then when we look at the CPU backend, we can see with additional metrics that NUMA and high DTLB are what are kind of causing them. So these are second level metrics that you can find as part of various tools that Intel has. So you can see that the iCache misses are 11%, the ITLB is 9%, and the DTLB load is around 12%. And then there are a variety of other metrics too that you can get from the performance monitoring unit. You can determine the utilization of the CPU as well as the utilization in the kernel mode and how much of the traffic is going on this 2-socket system to the remote socket. We can see that almost 40% of the utilization is in the kernel, and that's overhead that can be addressed through offloading techniques or variety of other techniques. And then the NUMA overhead is what is also causing the higher CPU backend, and I'll cover in the next couple of slides how those can also be addressed. And there are a variety of tools that Intel has from the vTune analyzer, and you can also get more details of the TMA breakdown in the Intel Architecture Optimization Manual. So let's look at how we can optimize through software for these kinds of issues that we just saw. So I'm going to cover 3 optimization techniques. The first one is path length reduction, which is if you think of a request that's coming to a microservices, it's going to execute some number of instructions. So in the Death Star bench, for example, each request takes about 7 million Intel CPU instructions. So you can reduce the instructions either through some algorithm changes in the workload, or through system and compiler optimization, or also utilizing a variety of instructions that are available on Intel CPUs and having a high ISA affinity. For example, with AVX512, you can use them for vectorization. The vector neural network instructions can be used for quantization, and the VAES instructions for encryption, and the AMX for matrix multiplication. The second set of optimization techniques are less familiar to software developers. So to optimize memory and cache, you can use the CPU and memory manager in Kubernetes to do appropriate placement of the services. And for the UARCH bottlenecks, you can use larger pages for the ITLB. And you can also relay out the code using Intel last branch record techniques that reduce the iCache misses. And then finally, the DTLB, you can reduce through using 2 meg or 1 gig pages. I'm going to show some examples very soon. And then the last set of optimization techniques is to be able to offload and accelerate very specific components. So you can offload data movement through the DSA. You can offload encryption and compression through QAT, etc. And the Intel Sapphire Rapids platform that we will discuss a little bit later has a variety of these capabilities. So we have some GitHub links for the optimization manual examples, as well as links for using code layout using the LBR, as well as large code pages, and the DSA specification, and also software that you can use with the DSA. So let's take a look at a concrete example. So this one is from a language runtime, the PHP language runtime, and the workload is the WordPress workload. And we're using two path length optimization techniques. We are using the VAES instructions which are the crypto new instructions for accelerating the HTTPS traffic, and also locking for improving the database operations. And a variety of CPU stall reduction. We are using large pages for both the instruction and the data TLB in both PHP as well as MariaDB. And we're using code layout for the instruction cache. And then we are affinitizing per socket the containers. So we have in the open source Docker files available for the base container and the optimized container. And what kind of performance improvement can you expect from something like this? So on our third generation Xeon Scalable, which is the Ice Lake servers, with the same core count as the Cascade Lake second generation server, the software optimization for both the path length and the CPU stall reduction, you can gain 83% or 1.83x gain. So in addition to the hardware gain, you can get substantial gain if you're able to optimize the relevant software component from existing techniques. Right? Software optimizations can deliver double-digit improvements. I'll now let Ravi conclude this presentation.
Thank you, Suresh. So we've heard from all the content so far on the importance of microservices, their characteristics, the challenges, as well as methods to both break down the latency and understand bottlenecks, and optimization techniques that can be applied and have been successfully applied to both runtime languages and other types of software to do optimization so far. Sapphire Rapids brings an extensive set of new capabilities that are uniquely suited to microservices, including discrete on-device accelerators that are well suited to the way microservices are developed, because microservices inherently break up functionality into discrete functions and services, and that is well suited to the way Sapphire Rapids actually implements these. And this applies end to end. So it isn't just about absolute performance, although that improves as well, but it's across the life cycle from deployment to operations to actual execution. And if you look at the examples shown here, Intel has been contributing to Kubernetes for a while now, and the device feature awareness in Kubernetes is being enhanced to ensure that all of the Sapphire Rapids features are there and are supported. And faster container spin up and tear down is a significant new capability, which will be possible through DSA, or the data streaming accelerator. If you think about auto scaling, any of those scenarios requires reading in the images for the containers and loading that into memory, multiple ones for most deployments. And that will be accelerated because DSA supports memory copies of sizes of 4K and above. And similarly, when you're scaling down or you're deallocating, you want to zero out memory, and that is also supported through DSA. My colleagues also touched on the value of the hardware telemetry in the performance monitoring units, and that has been enhanced significantly, including support for architectural LBRs, or last branch records. And communication is a very important part of any distributed microservice deployment, and that has been extensively accelerated with capabilities like QAT and DLB that are part of SPR, also on-device accelerators. And there's another Intel on session and a demo with the DLB capabilities that I would encourage you to go and watch. And we've also talked about the upcoming infrastructure processing units, or IPUs. Mount Evans is the first generation, which will also allow much more efficient operation with offloads, with capabilities for accelerators and also for shared virtual memory. And when we talk about performance itself, there's an extensive set of capabilities that are available. Suresh already talked about the runtime optimization that's possible. There's optimizations going throughout the software stack, as well as platform optimizations that will be going into the Linux kernel soon. And if you look at one of these and we dive into them, just in terms of performance, we covered some content around runtime languages and how we can optimize them. And there's also information here about a specific instruction set for user interrupts. This has been recently upstreamed into the Linux kernel and was featured in the Linux Plumbers conference. And I have the link down here for additional detail for anyone that's interested. But this is a mechanism that lets you bypass the operating system or the kernel, if you will, and send events directly to user space. And this overcomes significant limitations that exist today in terms of how IPC, or inter-process communication, is handled. And as the chart above shows, this is significantly faster than most other methods that exist today, like signals or pipes. Now, the fastest is when the user API is in running state and not blocked, meaning when a thread is communicating with something else and waiting, then it is normally blocked. So what would be the use case when you're continuing to run, but you can be interrupted in a low latency manner? And those are examples that we've listed here. Let's say that you get a much higher interrupt task that needs to be completed before what is being processed right now. That can be accomplished using this in a lightweight manner. Or if you want to reread configuration while the task is continuing to run, that is another use case, as well as generally improved gRPC latencies for multiple use cases. So this can cut across the board. This is an example of what is possible with one of the new instructions in Sapphire Rapids. And if you put it all together, this is our view of microservices performance estimated through Death Star bench on multiple generations of Xeon, going from Cascade Lake server to Ice Lake server to Sapphire Rapids. Obviously, Sapphire Rapids measurements were on early silicon, so we expect that to stabilize soon. But we expect improvements across all of these three areas. Improved performance and tail latencies with all of the changes and the enhancements that we spoke about. Lower infrastructure overhead, because the performance counters let you identify and debug and optimize where there are areas of overhead, as well as Kubernetes enhancements that let you place workloads, VMs, or containers in a much more efficient way, and faster communication with the combination of DLP, DSA, and others. And so if you look at the combination of all of these capabilities, this is a platform that should address the microservices challenges in a very meaningful way. And the resources and the links listed here will be made available so that you can follow up on these, and more to come on this. So thank you very much.